Yes, good morning, my dear friends, and welcome to physics online classes. Look here in the yesterday's class, we are discussing about the types of extrinsic semiconductor. In the yesterday's class, we are discussing about the types of extrinsic semiconductor. Look here, maybe you are completed the N-type semiconductor, and today we'll go for the P-type semiconductor. And before that, make up once again you recall or recap what you studied in the yesterday's class. And today we are going for the lecture number 5. We are going for the lecture number 5. And look here, I just said here, as you have completed the intrinsic semiconductor, in the intrinsic semiconductor there are some drawbacks. What are the drawbacks? That is, for low temperature it acts as insulator, and also the important thing, in the intrinsic semiconductor the number of holes and number of electrons are same. The number of electrons and number of holes are same. This is also one of the important drawback. And another most important thing, the conductivities are more. In intrinsic semiconductor, conductivities are more, not more. It means the conductivity is very less. To increase the conductivity, you are going for the extrinsic semiconductor. To increase the conductivity, you are going for the extrinsic semiconductor. As I said already, extrinsic semiconductor, nothing but it is also called as impure semiconductor. It is also called as impure semiconductor. It is also called as doped semiconductor. And as I said already, doping nothing but by adding the impurities to increase the conductivity. The doping is a process. By that process, by adding the impurities, we can increase the conductivity. That is nothing but doping. And extrinsic semiconductor is also called as doped semiconductor. And look here in the yesterday's class, you are discussing about the extrinsic semiconductor. Extrinsic semiconductor. In the extrinsic semiconductor, important thing, you have done two types. One is about your N-type semiconductor. N-type semiconductor. And second one is about the P-type semiconductor. P-type semiconductor. Here, I just said here, as we know, our semiconductors, if it is in the purest form, it is conductive, it is very less. To increase the conductivity, we are adding the impurities. And what type of impurities we are adding? We are adding what type of impurities? And depending upon impurity, you order the types of semiconductor, that is N-type semiconductor and P-type semiconductor. It means in N-type semiconductor, as we yesterday discussed, a pure semiconductor, and by adding the is pentavalent, by adding the pentavalent impurity. By adding the pentavalent impurities to the pure semiconductor, that is nothing but your N-type semiconductor. A pure semiconductor or your intrinsic semiconductor, by adding the pentavalent impurities, it may be your arsenic or it may be phosphorus, that becomes the N-type semiconductor. By adding the pentavalent impurities, that becomes the N-type semiconductor. It means yesterday we discussed already. Actually, in the N-type semiconductor, I said here, our you consider the phosphorus. Phosphorus having the 5 electrons. The phosphorus, because that is pentavalent impurity, it means they are having the 5 valence electrons. Actually, that phosphorus we are adding with our silicon. Actually, what happens? Our phosphorus of 4 valence electron and neighboring silicon of 4 valence electron, they will make covalent bond. They make the covalent bond, and you are having the one extra electron. You are getting one extra free electron that is not having any covalent bond. That is totally free from the covalent bond. It means in your whenever adding the pentavalent impurities to a pure semiconductor, you will get the more number of electrons are generated. You will get the more number of electrons are generated. It means if you add very small amount of impurity atom, especially if you are adding the pentavalent impurity, you are having the more number of free electrons. You will get the more number of free electrons, especially you are getting the millions of free electrons. And important thing is about, as you know already, the N-type semiconductor is also called as donors. The N-type semiconductor is also called as donors because they will donate one electron to the conduction band. They will donate one electron to the conduction band. That's why they are called donors. It will donate the one electron to the conduction band. And also important thing, you have studied in the last class, in N-type semiconductor, the electrons are magnetic carriers. It means electrons very more, but the holes are magnetic carriers. And we ask the question, sir, how will get the holes? No doubt the electrons will get from the, because of by adding impurities you will get the electrons. What about holes? Especially the holes will come because of your temperature, because of thermal energy. You can break the covalent bond and will get the electron hole coming pairs. But important thing, as I said, whenever adding the pentavalent impurities, keep it in mind, without creating the hole, we can generate the electrons. Without creating the hole, we can generate the more number of electrons. That is the importance of your N-type semiconductor. It means, yesterday I said in a good way, how to identify the N-type semiconductor. Look here, in N-type semiconductor is nothing but N-type. You are adding the pure semiconductor Si plus your phosphorus. Si having the 4 valence electron and you are having your phosphorus having the 5. It means actually what you want? 4 plus 1. It means this is one extra electron because this 4 of our phosphorus, they make covalent bond with the 4 of silicon, but one extra electron is there. This is not having any covalent bond with our silicon because it is totally extra, and this extra electron nothing but the free electron. That's why the N-type semiconductor is called as donors. They will donate one electron to the conduction band. They will donate one electron to the conduction band. This is about the very simple way to understanding about the N-type semiconductor. It means in N-type semiconductor nothing but a pure semiconductor by adding the pentavalent impurities. It may be phosphorus, it may be arsenic. And as we know, our silicon having only 4 valence electrons, phosphorus having the 5 valence electrons. 4 of silicon and 4 of your phosphorus, they make the covalent bond. But one is extra electron, that is nothing but free electron. That is totally free from the covalent bond, that is not having any relation with the parent atom. It is loosely bonded to the nucleus, that is they can easily move from the conduction band. They easily move in the crystal. And as I said, it is also called as donor level. And if you draw the energy band diagram of N-type semiconductor, this is the energy band diagram for your N-type semiconductor, and this is your conduction band, this is your conduction band, and this is your valence band. Important thing, as we know, here you have the more electrons as compared to this more electrons, you are having only less number of holes. We are having the very less number of holes. As we know, the holes are there in the valence band. This is nothing but your N-type semiconductor. And also important thing, this is called the Fermi level. This is called the Fermi level. And this energy I said 0.01 electron volt for the germanium and 0.05 electron volt for the silicon. This Fermi level, nothing but, as I said in the yesterday's class, the Fermi level What is Fermi level energy? Nothing but the maximum energy occupied by the electron in the absolute temperature. The maximum energy occupied by the electron in the absolute temperature. That is nothing but Fermi level energy. That Fermi level energy in the entire semiconductor, it is the below the conduction band. This is nothing but Fermi level energy. This is below the conduction band. This is the below the conduction band. And if you draw the actually what is there inside the entire semiconductor. In the entire semiconductor, important thing, you are having the electrons also there. You are having the electrons also there, like that, and also you are having holes are there, like that. You are having holes, and also no doubt you are having the electrons or magnetic carriers. But important thing, whenever you are adding the pentamer impurities to the pure semiconductor, and you are having the one electron, extra electron, and whenever you are adding the, for example, you are adding phosphorus, you are adding with the your pure semiconductor silicon, and it will give the one extra electron, and if you give it will give the one extra electron, and whenever it is giving that extra electron, that becomes the positive charge. That becomes the positive charge, because if that phosphorus they may give one extra electron, it means the electron come outside. That phosphorus atom becomes the negative charge. That phosphorus atom becomes the positive charge because electron come outside. It means that is also called as immobile ion. It means in your entire semiconductor, you are having the positive charge carriers. They are called immobile ions. Positive charge immobile ions. It means in the entire semiconductor, you are having the electrons and magnetic carriers and holes and magnetic carriers. Also, you are having the positive immobile ions. And how will you get the positive immobile ions? Whenever you are adding the phosphorus or arsenic, and whenever the phosphorus you are adding with the silicon, that phosphorus atom they will give one extra electron. And whenever it is giving the extra electron, that atom becomes the donor atom. That atom becomes donor atom, and it becomes the positive ion. That becomes the positive ion. It is also called as immobile ion. This is also called as, this is nothing but electron, free electron, and this is nothing but the hole. This is nothing but hole, and this is nothing but your immobile ion. Immobile ion. Why it is called immobile ion? It is not involving the conduction of the current. Why it is called immobile ion? It is not having the, it is not taking, it is not having the, in the conduction process, it is not having, you are not using the in the conduction process. In the conduction process, you are using only the electron and holes. You are not using that immobile ions. Immobile ions is no use in the conduction of the current. That's what it is called immobile ion. They are not moving. They are totally bound to the nucleus. It means whenever you are adding the pentamer impurities, that added impurity, that is called dopant. For example, you are adding phosphorus, that phosphorus is called dopant because you are adding with the pure semiconductor. And added impurity, they will give an extra electron, that becomes the immobile ion. Whenever they will give the one extra electron, that becomes the positive immobile ion. Because electron come outside, and if the electron come outside, that atom becomes the positive. That is nothing but positive ion. That is also called as immobile ion. This is the importance of your entire semiconductor. Another important property of entire semiconductor, the entire semiconductor is totally neutral. That entire semiconductor is also called as it is totally neutral. And this is about the importance of your entire semiconductor. Now we will go for the p-type semiconductor and how to construct the p-type semiconductor and what is the crystal structure of your p-type semiconductor. We will go for the p-type semiconductor. Go for the p-type semiconductor. We go for the p-type semiconductor. We go for the p-type semiconductor. Look here, as I said here also a pure semiconductor, by adding the trivalent impurities by adding the trivalent impurity. By adding the trivalent impurities is called your p-type semiconductor. Is called p-type semiconductor. It means, as I said here, if you are a pure semiconductor, if you are adding the trivalent impurities, maybe your boron or aluminum, that becomes the p-type semiconductor. It means a pure semiconductor by adding the trivalent impurities. It may be your boron or maybe aluminum, and that type of material is nothing but the p-type semiconductor. It means a pure semiconductor by adding the trivalent impurities. It may be your boron or aluminum, that becomes the p-type semiconductor. And if you draw the crystal structure, then you can understand very easily about how we can adding the impurities, especially when adding the trivalent impurities in pure semiconductor. You draw the crystal structure, then you understand very easily about the p-type semiconductor. Look here, as usual, you take the, in between you take the boron, this is your boron, and surrounding the boron you are having the silicon atoms are there. Yes, you are having the silicon atoms are there surrounding the boron, and here in the middle you take boron. You are having the like the covalent bond between the each atoms. These are all silicon. These are all silicon. Here, like we are having the covalent bond. Yes, we are having the covalent bonds, and next you take the, here you take the electrons of the different electrons are there. Here, what I am going to say here, it means here in the surrounding you are having the silicon atoms and you are adding the boron with the pure semiconductor. Look here, as I said, boron 1, 2, 3. Boron having the, it is a trivalent impurities. It means you are having only 3 valence electrons. Boron having the 3 valence electrons. Actually, this boron, what they will do? 3 of your boron, they make covalent bond with the 3 of our silicon. Actually, in silicon there are 4 valence electrons, but in boron having only 3 valence electrons. Because of these 3 of boron, they make the covalent bond with the another 3 of your silicon. It means in the 4th covalent bond, it is not complete. Because here we want another electron, but this electron is not there. This vacant place of position nothing but the hole. That vacant place of position nothing but the hole. This is nothing but your hole. This is nothing but 4. And as you know, this is your covalent bond. Covalent bond. The important thing, what is important about p-type semiconductor? Look here, as I said here, in the p-type semiconductor, a pure semiconductor by adding the traveling properties, especially by adding the boron. And if you are adding the boron to a pure semiconductor, as I said, boron having the 3 valence electron. These 3 of boron, they make covalent bond with the 3 of our silicon. But you are having only 3 covalent bonds are complete. You are having only the 3 covalent bonds are completed. You see here, actually here you want one extra electron. But you are not getting the electron, is not there because your boron and 1, 2, 3. They make here covalent bond. This 2, this 2, this 2, and this you are not having this here. Here you want another electron, but your electron is not there. It means this incomplete bond, or it is deficiency of electron, nothing but hole. It means keep it in mind. Whenever you are adding the travel impurities to a pure semiconductor, you are having you will generate the holes. It is also called as the p-type semiconductor is also called acceptor. It is also called acceptor because they will accept one electron from neighboring. And important thing here, to fulfill the covalent bond, what this hole will do, they will take the another electron. It means as you know, the hole having the property to attract the neighboring electrons. This hole, what they will do, they will take one electron from the neighboring to fulfill the bond. To fulfill the bond, they will take one electron from neighboring. That's why your p-type semiconductor is also called acceptors. They are also called acceptors because they will accept one electron from the neighboring to fulfill this bond. It means if you take the you take the boron and a pure semiconductor by adding the boron, then what happens? Your boron having only 3 valence electron. These 3 of boron and another 3 of silicon, they make covalent bond. But here we are having only 1, 2, 3 covalent bond. They are full. But this 4th covalent bond is not complete. It is incomplete. Because why it is incomplete? Because we want another electron. But here you are having only 1 electron. Another you are not having this electron. This deficiency of electron, this vacant place of the electron, nothing but the hole. It means whenever you are adding the more number of impurities, especially you are adding the travel impurities to a pure semiconductor, we can generate the more number of holes. We can generate the more number of holes. That's why in the p-type semiconductor is also called as the majority carriers are holes. The majority carriers are holes. And important thing, as I said here, why it is called acceptors? Because to fulfill the covalent bond, this hole, what they will do? They will attract this electron. They will attract this electron. And here, this bond will be completed. But here once again we are creating the hole. Here once again creating the hole. Like that, this process continues. Like that, this process continues. It means to fulfill the covalent bond, they will accept one electron from neighboring. That's why they are called acceptors. The p-type semiconductor is also called as acceptors. Why? Because they will take one electron to fulfill complete the bond. This is the importance of your p-type semiconductor. Keep it in mind. A pure semiconductor, by adding the traveling impurities, it means boron, aluminum, that becomes the p-type semiconductor. It means, as you know, in the surrounding you are having the silicon atom, but in the middle you are adding a boron atom. And as I said, you have to add the impurities that does not disturb the structure. Like that you have to add the impurities. And now we are adding the impurities. And as you know, boron having the 3 valence electrons because they are traveling impurities. They are having only 3 valence electrons. But our silicon having the 4 valence electrons. 3 of your boron and 3 of our silicon, they make covalent bond. But another one is incomplete. Another one is incomplete because we want another one electron. But you are not having that another one electron. This vacant place of position nothing but the hole. Or this deficiency electron nothing but the hole. It means in the overall the important about p-type semiconductor, no doubt you can write here the majority carriers. Majority carriers. Majority charge carriers. Majority charge carriers are holes. And also the minority carriers. Minority charge carriers or electrons. And also, as I said, the important thing about the p-type semiconductor, the holes are majority carriers, and as we know, hole is nothing but positive charge carrier. The hole is nothing but positive charge carrier, and as usual, the hole having the hole is positively charged. That's why it is called p-type. Why it is a p-type semiconductor? Because they are having the majority carriers of holes, and also the p-type semiconductor, they will give the more number of holes. They will generate more number of holes, and holes having the positive charge. That's why it is called p-type semiconductor. Yesterday I said why the n-type semiconductor. Why it is called n-type semiconductor? Because in n-type semiconductor, electrons are majority carriers and electrons have the negative charge. That n indicates negative charge. Here the P indicates your holes are positive charge carriers. This is about in a simple way of your p-type semiconductor. Another important thing, as I said here, whenever you are adding the impurities to the pure semiconductor, that added impurity, for example, you are adding the boron, that boron will give one hole, they will give one hole, and whenever it is giving the holes, means they will generate the holes, that boron atom, that becomes the negatively charged particle. That is nothing but another important thing. You can write here the boron. You can write here the boron. That is nothing but it is actually a negative ion, or it is acts as a negative immovable ion. Why it is negative immovable ion? Because it is giving the more holes. If that atom having the holes come outside, it means that atom becomes the negative ion. And whenever we are adding the trival impurities, especially we are adding the boron, aluminum, that added impurity, they will act as an immobile ion, and that is totally filled in the, you are totally bound to the nucleus. That is not having any. It is not used in the conduction of the current. The immobile ion is no use in the conduction of the current. Only the conduction current in semiconductor, it may be because of electrons or because of holes. Why it is called immobile ion? Because it is not having any current conductive place because of the immobile ions. That is called immobile. They are unmoving. Current is not because of these ions. Only current is because of holes and electrons. It is called negative immobile ion. Why you get negative immobile ion? Whenever you are adding the trival impurities, that added impurity, that whenever they are giving the holes, extra holes, that if the holes come outside, that atom, that especially that boron or aluminum, that acts as a negative ion. This is about the importance about the p-type semiconductor. And if you draw your energy band diagram, how will you get this? The important thing is about, as usual, this is your energy band diagram. Here you are having this is nothing but your conduction band, this is nothing but conduction band, and this is nothing but valence band. And important thing here, having the more holes, and here only small number of electrons are there in the conduction band. And here the important, this is your Fermi level. This is the Fermi energy level. This is nothing but your, I said SI it is for 0.05 electron volt, and for germanium it is 0.01 electron volt. It is nothing but your Fermi level. It means it is your p-type semiconductor, and in the p-type semiconductor what happens? The holes are majority carriers. Holes are more in the valence band, and very less numbers of electrons in the conduction band. It means in the p-type semiconductor, the majority carriers are holes and minority carriers are electrons. And also important thing, as compared to your valence band and conduction band, especially the Fermi level, that is very near to the valence band, and also it is above the valence band. The Fermi level is above the valence band. The Fermi level is above the valence current. This is about importance of your p-type semiconductor. And as I said already, the p-type semiconductor is electrically neutral. It is electrically neutral. Why it is electrically neutral means, look here, this is your p-type semiconductor. As I said here, it is having the, no doubt, it is having the holes of magnetic carriers. And also, as I said here, they are having the electrons also there. They are having the electrons also there. And also, you are having the some negative immoral ions. They are having the negative immoral ions. They are having the like that negative immoral ions. This is nothing but your p-type semiconductor. It means, as I said here, no doubt, in the p-type semiconductor, the holes are magnetic carriers and electrons are magnetic carriers. And also, you are having the negative immoral ions. Why you got negative immoral ions? Because the dopant, what you are doping, the dopant, you are adding that impurity, it may be your boron ion, that acts as an immoral ion. That acts as an immoral ion. Whenever they given, you are added the impurity, that added impurity that acts as an immoral ion. That added impurity that acts as immoral ion. It means in the p-type semiconductor, no doubt, the holes are magnetic carriers and the electrons are magnetic carriers. And also, you are having the immovable ions. This is about the importance about the p-type and n-type semiconductor. The most important thing in p-type semiconductor, if for example, as I said here, you are adding silicon and you are adding a boron. As we know, silicon having only the 4 valence electron, boron having the 3, and 4 plus 3 we are having 7. But we want 8. We want 1 minus 1. We want actually 8. 8 minus 1. That is nothing but 7. It means you are having 1 electron. We are not having the losses of 1 electron. This lossing of 1 electron nothing but the deficiency of 1 electron nothing but the whole. The deficiency of 1 electron nothing but the whole. If you are semiconductor, by adding the travel impedance, 4 plus 3 7, but you want 8. It means to make it the fulfill the covalent bond, we want 8 electrons, but we are having only 7. One deficient electron nothing but the whole. This also you can say mathematically say about the p-type semiconductor. It means in p-type semiconductor we are adding a boron to a pure semiconductor. Whenever adding a trivalent impedance to a pure semiconductor, what happens? Your boron aluminum, they are having only 3 valence electrons. They are having only 3 valence electrons. It is not actually, as I said, it is gold. It is having only 3 valence electrons. And this 1, 2, 3, these 3 of boron, they make covalent bond with another 3 of your silicon. But here, actually to make it covalent bond for the silicon, they want another electron. This silicon, they want to make it covalent bond, they want another electron. But here you are not having an electron. Here you are having the deficient electron. Here is vacant place of the electron. That vacant place of electron or deficient electron nothing but 4. It means whenever we are adding the traveling impedance, we are having the more number of holes. We can generate the more number of holes. That's why the p-type semiconductor is nothing but the majority carriers are holes. The majority carriers are holes and they are having the positive charge carriers. Holes are called positive charge carriers. That's why it is called p-type semiconductor. And also important thing, the p-type semiconductor is also called as acceptors. This is called acceptors. Why these are acceptors? Because to fulfill this complete the band, complete the bond, they will take 1 electron from neighboring. Now 1, 2, 3, these 3 bonds are complete, but its 4th bond is not complete. It is incomplete bond because we want another electron. You are not having another electron. Then what they will do? This hole they will attract 1 electron from neighboring. Then it completes this bond. That's why it is called acceptor. They will accept 1 electron to fulfill the bond, to make it the complete bond. They will take 1 electron from neighboring. That's what it is called acceptor. They are called acceptor. This is about the importance about the p-type semiconductor. Now we go important. What is the difference, the comparison or the difference between the p-type and n-type semiconductor? The difference between the p-type and n-type semiconductor. Can say about difference between n-type and p-type semiconductor. P-type semiconductor. This is a very important question for your You can write the table if you want. This is P type and this is N type. This is very important 3 mark question for exam. What are the difference between the N type and P type semiconductor? As usual, we know in N type semiconductor we are adding the pentavalent impurities. The first one, adding the pentavalent impurity, and here we are adding the trivalent impurity. And as usual, in N type, yes, the electrons are more, majority carriers. Electrons are majority carriers. But here the holes are majority carriers. Holes are majority carriers. And also, as usual, we know in the N-type semiconductor, as I said here, the density of electrons is more, and here density of holes will be more. The density of in N-type semiconductor, density of electrons very more, and here the density of the hole will be very more. I connect here the Ne connection R1. The Ne is greater than NH. Here the Ne is less than NH. And also the important thing is about the Fermi level. As I said here, in the N-type semiconductor, the Fermi level is near to the conduction band. But in P-type semiconductor, the Fermi level is near to the valence band. In N-type semiconductor, the Fermi level is near to the conduction band, and in P-type semiconductor, the Fermi level is near to the valence band. And also important thing here in the N-type semiconductor, most important thing here, the majority carriers are electrons and magnetic carriers are holes. And here the majority carriers are holes and magnetic carriers are electrons. And this is about the difference about N-type and P-type semiconductor. Can write any 3 or 4. And important thing as I said about in your N-type semiconductor, we are adding the pentavalent impurities. I can write in example also. You can write silicon or germanium. You can write here another 4. You can write silicon. Sorry, you can write your phosphorus or arsenic. Here you can write boron or aluminum. We are adding the trivalent between boron and aluminum. Here may be the phosphorus or arsenic. It means in boron N-type semiconductor we are adding the pentavalent impurities, and in the P-type semiconductor we are adding the trivalent impurities. And important thing here, the electrons are majority carriers, and here the holes are majority carriers, and here the holes are magnetic carriers, and here the electrons are the magnetic carriers. And also important thing, here electron density is very more, and here hole density very more. And important thing another I said about in N-type semiconductor, the Fermi level it is near to the conduction band. Here the Fermi level is near to the valence band. And important thing about another important thing, in your N-type semiconductor, the electrons are having the mobility of electron very more than the mobility of the holes. And that also an important thing about the N-type and P-type semiconductor. This is about the N-type and P-type semiconductor. No doubt, I just said, it may be the N-type semiconductor or it may be P-type semiconductor, they are electrically neutral. Why the P-type semiconductor or it may be N-type semiconductor, they are electrically neutral. No doubt. Here in P-type semiconductor, holes are the majority carriers. But in N-type semiconductor, electrons are majority carriers. Still, the N-type semiconductor or your P-type semiconductor, they are all called neutral. Why they are called neutral? Because we are adding the impurity that is neutral. We are adding the impurity that is neutral. For example, maybe arsenic or maybe we are adding the boron, they are all neutral. This is about the importance about the P-type semiconductor and N-type semiconductor. Actually, if you take alone, individual take P-type semiconductor or N-type semiconductor, that is no use. If you take individual P-type semiconductor or N-type semiconductor, no use, because P-type semiconductor is electrically neutral, N-type semiconductor is also electrically neutral. If you combine both the P-type and P-type semiconductor and N-type semiconductor, there are so many advantages. And how you are combining, how you are connecting, or what is the effect of if you combine the P-type semiconductor and N-type semiconductor, That is so important concept. We go for that is nothing but the PN junction. How we are combining or how we are adding the PDA semiconductor and the semiconductor. We'll go for that in the next class. Thank you.